Today I'm going to discuss Einstein's 27 worst special relativity mistakes. And these are from the perspective of a quantum field theorist. And I'll start by saying that, of course, we have to take the speed of light limit for objects into account when we're measuring things like velocity, energy, and clock rates. So there are relativistic phenomena that have to be calculated in the usual manner. I'm not saying that all relativistic effects can be ignored, because they can't. But Einstein went about some things completely the wrong way and came up with a wrong interpretation of the physical reality. And so that's where I want to start with, is the physical reality based on quantum field theory. So number one, and by far his biggest mistake, is Einstein denied the existence of the quantum field. We know now that the quantum field exists, so his denial was off base, and it led to numerous other difficulties. So what he assumed was that we had, in literary terms, space being a boundless container that contains all matter. Space by itself, in a literary sense, is non-physical. It's just an abstract concept of a non-physical container that contains everything. And the universe is similar. The universe is a boundless abstract container that contains everything. For number two, we have the problem that he claimed that this non-physical space has physical dimensions, which is a logical impossibility. Non-physical space can't have physical dimensions. And he, and relativists since, have never explained how non-physical space can develop physical dimensions. They just assume that it does, magically, like pixies sprinkle pixie dust and space gets physical dimensions. And similarly, three, he claimed that non-physical space is clocks. And once again, there aren't pixies hanging clocks everywhere. And Einstein never explained how his imaginary clocks emerged from space. And no one else has either. They just say, oh yeah, space has clocks, and everyone pretends like they know what the hell they're talking about when they don't. 4, what he missed was that dimensions emerge from the quantum field. The quantum field contains quantum fluctuations. Quantum fluctuations have wavelengths and frequencies. Wavelengths we measure in meters, frequencies in cycles per second. So quantum fluctuations have dimensions, and they have clock rates. And so 5, he missed that clock rates emerge from the quantum field. And how they emerge is interesting, that the quantum field contains particle paired dipoles. And we know it contains dipoles because of the Casimir effect, which is due to van der Waals forces. But that means there's van der Waals torque. And van der Waals torque is what limits the motion of charge and regulates the motion of charge, including the dipoles, the quantum dipoles themselves. So the wavelengths and frequencies are regulated by the van der Waals torque of the quantum field, which determines the dimensions and clock rates of the quantum field. And in that way, dimensions and clock rates emerge from the quantum field. It has nothing to do with non-physical space. It's a quantum field effect. And the other thing about that is, number 6, the dimensions and clock rates are electromagnetic. They emerge as electromagnetic phenomena in accordance with quantum field theory. and specifically Planck's theory of harmonic oscillators. But that means 8, special and general relativity are electromagnetic phenomena. Now I'll talk about general relativity more in the next video because there's so many mistakes with general relativity I couldn't combine them with all the special relativity mistakes. But we have a case where instead of talking about space somehow being separate from electromagnetic phenomena and having emergent properties of distance and time, the distance and time emerge from quantum field under quantum field theory, which makes all of relativity theory electromagnetic in nature. And if you start from this basis, then unifying relativity theory with electromagnetic theory is trivial because you start with electromagnetic phenomena. And that's what we must do as physicists if we're going to actually have an accurate physical system or understand nature's real physical laws rather than man-made fictitious things like non-physical space having physical dimensions and clocks. Then we have 9. The quantum field has a rest frame. It has a frame of reference where the permittivity and permeability are at their lowest and the speed of light is at its highest, as Maxwell first suggested. So we have to include a physical rest frame when we're doing frame transformations. And Einstein denied that there was a rest frame because he denied the existence of the quantum field, of a quantum type ether. Now, actually, just step back a little bit and be fair, the development of a quantum field as Planck oscillators was just in its earliest stages in 1905 when he published his paper. In 1906, Lorentz discussed the possibility of it, and it wasn't really till the 1930s that it fully developed. So while he made this big mistake at the time, there was still time to correct it later on, but people never went back and did it. Then we have the issue of 10. The dimensions and clock rates are fixed in the quantum field rest frame. The rest frame determines what they are. Now, in general relativity, they vary depending on the distribution of matter. Where all the suns and galaxies are actually change the physical constants, starting with the permittivity and permeability, which changes the speed of light. I'll talk about that more in the general relativity video. But in the special relativity sense, where we assume basically that there's no matter anywhere, we have a uniform set of dimensions, flat space everywhere, with a uniform clock rate in the rest frame. It's basically a Galilean type system for frame transformation. So that gives us 11. The rest frame is a universal rest frame with respect to relativity corrections, which means that when we're doing frame transformations, we have to, or we can, transform from one frame, reference frame, to the rest frame, to the other reference frame. And this prevents us from getting into paradoxical type problems. And I could have listed that as a mistake, that if you come up with a theory that produces paradoxes, then it's a wrong theory. So next we have 12. Space and the quantum field don't length contract or curve. The rest frame dimensions are the same. So you don't have physical changes in the quantum field rest frame. And space is non-physical, so it doesn't have physical dimensions to begin with, so they can't change. So that means we have to come up with a totally different perspective. Einstein's thought experiments were completely wrong on this. And to go with that, space and the quantum field don't time dilate. Their clocks, the clocks of the rest frame, are uniform because the distribution of frequencies of quantum fluctuations are uniform based on the uniformity of, on average, of the quantum van der Waals torque that regulates the clock race. And then we have 14. Moving observers don't change the quantum field dimensions. He thought that a different moving observer in a different frame of reference would cause the frame of reference to length contract in the direction of motion. Well, none of that happens. The actual quantum field is not affected by a moving observer, other than by the mass of the moving observer. But then we have an issue where they're just moving through space and they're not affecting the dimensions. They are causing an interaction that's related to inertia, but they're not causing the dimensions to change. But what they do happen is as part of that inertial reaction, we have 15. Moving observers experience more torque. So as they try to move through space at a velocity relative to the rest frame, they develop a torque because it causes the quantum dipoles to move, to rotate. And when they rotate, their rotation's resisted by all the other dipoles, which is where inertia comes from. And so this buildup of additional inertial energy means it takes more energy to accelerate. And which means when we have energy and acceleration, as we approach the speed of light, we have to take those relativistic effects into account in the math. But that doesn't mean that space is changing dimensions. And so what happens is 16, that motion increases the permittivity and permeability, the electric and magnetic constant. At least to the observer that's moving, it appears that the permittivity and permeability have increased because the torque on them has increased. And then 17, increasing the permittivity and permeability decreases the speed of light. So we actually do have an effective decrease in the speed of light. You get a lower distance traveled for the same amount of energy. So we have to make corrections to the distance traveled by a body that's approaching relativistic velocities. You can't just say it travels the speed of light in reference to its frame of reference, or a frame of reference that isn't the rest frame. All this gets really tricky when you dig down into the math of any given problem. But we have 18, motion slows clock rates of moving clocks. So the increase in the quantum van der Waals torque causes the clock rate mechanism of physical clocks to slow, whatever it may be, because this torque affects everything electromagnetically. And we already know that physical clocks do slow when they're accelerated, and this has been shown experimentally. The GPS satellites show that it's true. But once again, it has nothing to do with time dilation of space. It has everything to do with physical clocks interacting with the quantum field in such a way that the clock mechanism is slow. And we can calculate this using the equations that we use already. But 19, we have moving objects don't length contract. And this is another mistake that came about because of the way they interpreted space contraction, that they thought space contraction would make objects length contract. But if space contraction doesn't occur, then length contraction doesn't occur. And this goes back to even a bigger problem that I ran out of space to list, is you can't apply time dilation and length contraction together in the same problem. And because if you do, you get the wrong answer. And that's something that occurs in certain problems in relativity theory. And it's something that Einstein recognized and wrote about in a 1907 paper. He said that in the Michelson and Morley experiment, that if you applied both a time correction and a length contraction correction at the same time, you get the wrong answer. So he said only the time correction is necessary. Well, as I'll discuss in a minute, even that wasn't necessary for the Michelson-Morley problem, but it is necessary because we're aware that clocks do slow, but links don't contract. And we know that because 20, the Bohr radius and other radii are constant. And this is something, if you go through the electromagnetic relativity equations and you look at the Bohr radius, you find that the Bohr radius is constant. It has made of two terms that actually the relativistic effects work in the opposite direction, so they cancel. If you look at the Bohr radius under normal special relativity, you get the problem that they don't cancel, and so the Bohr radius has to get smaller. And so the idea that you get length contraction in one dimension is wrong, because you get length contraction in all three dimensions under Einstein's relativity. But in reality, there's no length contraction. And 21 is another problem, is that moving objects don't gain mass. And this is another false assumption that Einstein made. What happens in electromagnetic general relativity is that if you have mass locally increasing the torque, which increases the electric and magnetic constant, which decreases the speed of light. And since E equals mc squared, or m equals E over c squared, as you decrease the speed of light, you increase the mass, which would decrease the speed of light, which would increase the mass, which would decrease the speed of light, which would increase the mass. So you get in an infinite loop. So Einstein missed that if you use relativistic mass, or if there is relativistic mass, that it blows up general relativity theory. So in reality, we can't think of mass increasing relativistically. Now you can still use it for certain types of calculations if you want to, but in a real sense, we shouldn't think about relativistic mass. We're looking at relativistic energy, kinetic energy, or relativistic momentum that we have when we have velocities that are approaching the speed of light. And those are things that we must consider, and we can use current equations for some of that. But we don't have a real gain in mass. And then stepping back to Michelson-Morley experiment, one of the reasons it didn't work the way they thought is 22. The electric and magnetic constant are not directional. The electric and magnetic constant are the same regardless of which way the photon is traveling. They don't vary in one direction or another, depending on motion. Which leads to 23. The speed of light is not directional. And this gets to the heart of why the Michelson-Morley experiment didn't produce results. Because speed of light is based on the electric and magnetic constant. Permittivity times permeability equals 1 over c squared. That's how it works. Then another problem with the Michelson-Morley experiment was the assumption that light can travel in any reference frame. Light, 24 is, light travels in the quantum field rest frame. And that's because the photon is producing electric and magnetic fields all the time. So it's interacting with the quantum field all the time. So the instant a photon leaves the source, it's interacting with the quantum field. All it knows is the quantum field. So all it really sees is the quantum field rest frame. And then when it hits a detector, it gets stopped at the detector, but it jumps from quantum field rest frame to detector. So we need to think of the photon only experiencing the quantum field rest frame while it's traveling. And once again, the quantum field rest frame is uniform in all directions, with the torque being uniform and the magnetic and electric constant being uniform. So then we have 25. Light does not propagate at the speed of the source. It propagates at the speed relative to the quantum field rest frame. And the source velocity doesn't matter except that it causes an energy shift. And I could have added that to the list, that light leaving the source only experiences a Doppler energy shift. It doesn't experience any other relativistic phenomena. And you don't make any calculation on the velocity of the light based on the velocity of the source. And then 26 we have, the speed of light, c, is not constant. It actually varies based on the quantum van der Waals torque and the local permittivity and permeability, which gives us the speed of light. So the speed of light, 27, is not intrinsic to photons. It's a property of the quantum field. And it's actually a tertiary property. Number one, we have the van der Waals torque, and then 2, we get the electric and magnetic constants, and 3, we get the speed of light. So Einstein assumed that the speed of light is one of the most elementary constants when it's not. And which is another one of his big mistakes that I didn't have in the list. So that's my list here, and I didn't even get into problems with the mathematics of the equations itself and all other problems that have cropped up when people actually try to apply special relativity in various problems. So this list could be extended quite a deal, and I know have friends who study relativity theory who could certainly take a crack at it. But what I wanted to try to do was express some of the most elementary problems that are related to quantum field theory that I see as a quantum field theorist. And so what we must do when we think about special relativity is we need to go back and look at the constraints of quantum field theory, electromagnetic quantum field theory, and develop an entirely electromagnetic form of special relativity that only deals with what's really going on based on quantum field theory. And this list of problems should give you enough guidance that you can go through that yourself if you're a physicist who's skilled at understanding relativity theory. So I hope you enjoyed this video, and if you do, please like, share with your other physicist friends, and please subscribe so that you can get more of my videos in the future. And I also have my books on quantum field theory and my more recent book on particle theory. And I discuss relativity a little bit in my book, The Zero-Point Universe, and a little bit in the other two books as well. So maybe you'll enjoy those, and if you buy one of my books, that helps support me. I'm an independent researcher, so I appreciate all the support I can get. And I also have a Patreon account. So thanks for watching.